by calculator. So the first thing that you need to understand is what is a logarithm. This is something you haven't done in math class before. We didn't do these in Algebra 1. It's not an Algebra 1 concept. So this is one of the few things that's not really connected as directly as a lot of things we've done to things you did in Algebra 1. So a logarithm is one of the basic understanding of it is a logarithm is an exponent. Okay, so this equation here that I've got under there, it says log, and then in the subscript there is the base, and then of y is equal to an exponent. So that's a logarithm on the left side. It's equal to an exponent. Okay, so one of the things we're going to be doing today is taking expressions or equations and rewriting them as logarithms, or rewriting a logarithm expression as an exponential expression out of that. So the relationship with logarithms is all about exponents and exponent rules. So what you want to be thinking about as we're doing some things here is that logarithms act like exponents. So that's what we need to remember. Exponent rules are going to be part of the game. Okay. All right. Now,
I'm trying to get this to where I can write because it's on that side.
how about just close the computer?
Well, because it's like in my way.
Yeah, it's not anymore. Okay. All right. So let's talk about how logarithms and converting them back and forth between logarithm statements and exponential statements. Okay, that's the first thing that we're going to do. So easy thing. It's actually no calculation involved. It's all just moving things into the right spot. So it's kind of like puzzles. It's all it is. So write the logarithm as an exponential. Okay, and it's all based on this equation up here. The base, log base, is going to be the base of the exponential. What it's equal to is going to be the exponent that goes on that base. All right, so take the first example here. Something log base 2 of 8 is equal to 3. Okay, that's the logarithmic statement. We want to convert that into an exponential statement. The exponential statement is easy to do. Remember, a logarithm is equal to an exponent. So what's the exponent for this problem? 3, because the logarithm is equal to the exponent. The base of the exponential is the same as the base of the log. So when I read this, it's log base 2. So that means the base of the exponential is 2. So 2 with an exponent, we Lily said that the exponent was 3. That's correct. And then it's equal to this stuff, whatever's inside of that log there, 8. And that creates a true statement, right? 2 to the third power is 8. We know that that's true. But what we're doing here is just rewriting this logarithmic statement as an exponential. Why in the heck are we doing that? The reason we're doing that is eventually we're going to get to where we're solving equations that have logarithms in them, and we'll solve equations that are exponentials. If we can rewrite them as one or the other, sometimes it makes the equation even easier to do. Okay, so that's what we're trying to build skill level to be able to do. So let's take log base 3 of 81 is equal to 4. Let's write that as an exponential. What's the base? 3. What's the exponent? 4. It's equal to 81. It is that simple. It really is, this first thing that we're doing. Well, no. I can't say that it gets tougher. You guys know how it always starts out real easy, and then we get tougher. Absolutely. I will never say no to that. Will, could you help us out, please? Turn the arrow. Yeah. All right. Log base 5. And so let's throw some variables in there so that it's not a number expression. So it really starts making more sense that, hey, we're leading up to doing some equations later, which is what we'll do tomorrow. Okay, so let's rewrite this as an exponential statement. The base is, the exponent is, it's equal to, easy. This stuff is easy, right? Until they do this. Y'all know it's coming. Nothing new. Y'all know it gets tougher. Now, here's where knowing some things about logarithms comes in. And you guys, you've never seen logarithms before, so you don't know a whole lot about them. We're just trying to learn those things, okay? So when all of the first three examples, they had a base written there. This next one doesn't have a base written there. And it's an understood 10, okay? Anytime it's log with nothing written there, it's understood that there's a 10 there. The reason it's understood that it's a 10 there is because we live in a base 10 number system. Because, you know, when you write out a number, I'm going to mark this over here. When you write out a number like 367, right? This is the ones digit, right? What digit is this? Tens, and this is the hundreds. Another way of writing that is 10 squared is hundreds, right?
Never seen that before.
Oh, bless your heart. Elementary school teachers, you gotta get on the ball. This is what y'all supposed to know. Okay? That's 3 100s, 6 10s, and 7 1s. Base 10 number system is every digit is some sort of power of 10. The ones digit is 10 to the 0 power. Because anything to the 0 power is what? 1, right? So this is 7 10 to the zeros, 6 10 to the first, 3 10 to the seconds. That's what makes that number up. We live in that number system. You do math with that number system. Okay? Now, if you do computers and electronics, binary number system is base 2. And so if you're interested in that sort of thing, you can start studying about base 2 number system and how that works. It would help you in further in that. But it's an understood 10. If you just remember that if it's a plain log, nothing's written there, it's understood there's a 10 there. It's kind of like when when you have x, what's always in front of there, it's understood that there's a 1 there, right? It's the same idea, okay? Just remember, there's a 10 there. So when you rewrite that as an exponential, it's 10 to the third equals 1,000. Because 10 to the third power is 1,000, right? What that is called, it's called a common log. Common logs are logs that have a base that we are used quite often. Base 10, we're in a base 10 number system, so base 10 is common, right? Now, the one that it's a common log, but it's not as common to you guys probably as it is to maybe science teachers or something. That's LN, and I wrote it in cursive because that's how I learned to write. So LN is what that is. Sorry about that. I don't think about that. Did y'all learn to write in cursive? Okay. Because there's a gap there where they didn't do it for a few years, and then I think they've started back. So LN is what's called a natural log. And it seems like it'd be NL, but it's LN. Goes back to Greek words and all that stuff. But what it really is, it's a log base E. And these are just memorized facts. There's no fancy thing that says, hey, that's what happened, or a mathematical process that makes that happen. You just need to memorize these things that's happening. It's like you memorize the alphabet. Why is A come before G? That's how they set it up. Okay, so this is one of those things. This is how they set it up. Okay, when you see natural log, remember that's log base E. That's what you need to remember. Okay, so if we're going to rewrite that as an exponential, then it's going to be e to the 5th equals 148, 413. Now, e is about 2.7 and some change, a lot of decimals after that. E is a number that's used quite often in it's natural log because it's used a lot in sciences with biology, bacterial growth. It's exponential. That number E comes up enough that it's got its own variable that represents it. It's kind of like pi. Pi's got a representative. Instead of writing 3.1459 and all those decimal places that go after it, we write the symbol pi. E is the same idea. It's a number that's used enough in some context that it got its own representative. Instead of writing that number out every time, we just write E. It's the exponential number. So that's why they picked E. All right. So natural log is log base E. That's what you've got to remember that. Okay. And converting from natural log to exponential, it's the base is an E. So those are just memorized facts and things out of that. All right. Let's go the other direction. Let's take an exponential statement and try to write it as a logarithmic statement, which is the next hurdle to jump. Write each exponential as a logarithm. Example F, 5 to the third power is equal to 125. We're going to rewrite that as a logarithm. We need to know what log base to use. So what's the base in that exponential? 5. So we're going to use log base 5. So it's just a little subscript down there. And then this thing is going to be equal to the exponent, remember, because a logarithm is equal to an exponent. What's the exponent in that exponential? 3. So the 3 goes over there. So what has to go in the blank spot? 125. Do another easy one. 6 squared is equal to 36. It's definitely true, right? 6 squared is 36. Let's rewrite it as a logarithm. What would it be? Log base 6 of 36 is equal to, okay, 3 to the x is equal to 30. Write it as a logarithmic statement. Log base what? 3 of 30 equals x. Ten to the fifth is equal to 100,000. Write it as a logarithmic statement. What is it?
Log base 10.
It's 5. And notice I did not write the 10 there because it's understood to be there. Okay. Would I count it wrong on a quiz if you wrote the 10 there? No. But understand on a multiple choice type scenario, like on your EOC, they're not going to put that 10 down there as the base. You've got to understand that it's there. Okay. Easy stuff. This is cake right now. All right. Let's do E to the first. 2.71. So there's that E. So what log do we use? Alien, natural log of 2.71 equals 1. Now, I will count off if you write log base E, because that's not an accepted format. Okay. Log base 10 is accepted, but natural log and log base E, even though they're the same thing, log base E is not a notation that is accepted. All right. Now, being able to rewrite these logarithm statements as exponentials or exponential statements as logarithms can help us evaluate some things without a calculator. And you're saying, okay, well, why would I need to be able to evaluate things without a calculator? Well, there is a portion of your EOC that is no calculator allowed. So that's one reason. Another reason is that it really helps you understand why logarithms, what they do to numbers. Okay. Logarithms, one of the things that they can do and be used for is to take really extremely large numbers and make them smaller so they're more manageable and easier to calculate with. And it can also take really, really tiny numbers like a decimal point and like 55 zeros and then some numbers after that. If we can write that as a logarithm, we can take that number and make it a little bit more manageable, something, what we're can more easily see what's going on with the mathematics on that. So let's look at evaluating some logarithms without a calculator. And I will show you how to do that. Evaluate, A in it, without. And then we'll do some with the calculator as well. So log base 4 of 16. So they're just going to give you this statement. It's not an equation. We're just given this statement and told to evaluate that. So when we think about that, what we've got to be thinking about is, okay, what does that even mean? So one of the best ways to make that mean something more intuitive to you is to turn it into a logarithmic equation, like what we just did. Okay, so if I don't know what the answer is, so I'm gonna make it a variable. Just call it x, right? Pick whatever variable you want to. Steer away from I and O, but the other two, any other letter works. Okay, now can I rewrite that as an exponential? 4 to the x equals 16. Hey, I know something about 4 and 16. What do I know about 4 and 16? 4 squared is 16. So what does log base 4 of 16 have to equal? 2. So by being able to rewrite it as an exponential, it helps me to think about what numbers are happening, and I can get the solution to that without typing it into the calculator. Okay. Example L, log base 2 of 32. We're going to evaluate that. So if I think about that as a problem that I rewrite as an exponential, it'd be 2 to the x is equal to 32. What do we know about 32 in relation to 2? Well, 2 goes into it, right? How many times? It's 2 to the what power? 5 power. That's what's going to happen here. If you don't know those, think about doing this. Y'all remember doing factor trees? Not a hard thing to do, but once you get done, 1, 2, 3, 4, 5. That's how we're getting 2 to the 5th power, is how many, it's what 32 really is. So this is 2 to the x is equal to 2 to the 5th. Well, x has got to be 5. So log base 2 of 32 has to be equal to 5. Just by thinking about it. Now I'm writing all these steps down. If you can do that in your head, wonderful. If you got to write it out, fine. It's okay. Nothing wrong with you if you got to write it down. Let's look at another one. Log base 3 of 27. Evaluating that without a calculator. Now the numbers have to be special numbers for you to be able to do this without a calculator. When they're not so special, we got to use some technology to help us here. So if I think about that as an exponential, 3 to what power is equal to 27? 3. So this has got to be equal to 3. So I'm just thinking exponentially because we're dealing with logarithms. And what you've got to be thinking about is exponents. When you're dealing with logarithms, they're exponents. So that's how you've got to be thinking as you're doing this stuff. Okay, is exponents. All right. Let's look at evaluating with a calculator. So we've seen how we can manipulate things so that we can evaluate some stuff with a calculator. If we evaluate with a calculator. Log base 2 of 12. All right. Now, I would know that I would have to do this with a calculator because I know 2 goes in 12 6 times, but then that doesn't turn into a power of 2. It turns into 6 is 3 times 2, so I have a 2, and a 3. So I can't turn 12 into 2 to the 4th power or something like that. So I know that this can't be done without a calculator in that way, in the same way that I did those other 3. Okay, so to do this with the calculator, there's 2 different ways that we're going to talk about doing it. One way is using the log base function on your calculator. All right, so I'm going to show you how to do that. So on the graphing calculator, let me get rid of this real quick. On the graphing calculator, if you look down the left-hand side, you've got a log button, you've got a natural log button, but this is log base 10 and this is log base E. We're dealing with log base 2 in this problem, so we need to do a different base. So what I've got to do is hit the math button. Hit math, and then press the up arrow because log base is down at the bottom. And I'm choosing log base. Just hit enter. It should give you an empty box to put your base in and an empty box to put what you're taking the log base whatever of. Okay, so I'm doing log base 2 of 12. Just hit enter. And I get 3.584962501. There's a bunch of decimals after that. It just cuts off there out of that. So we're going to round that to 3 decimal places. That's pretty common practice. So approximately 3.58, and then look at the decimal. The 9 makes the 4 go up 1, so 5. This is the solution to that. Okay, that's using the log base. Another method is called the change of base formula. Change of base uses your common logs. The log of the number, log base 10 of the number divided by the log base 10 of the base. So with that, I don't have to go through the menu system to get it to do it. I can use the button that's already here. Most scientific calculators have a log base 10 button on them, like these little guys like this have that on there. They don't have the log base function out of that. So this is kind of one of those things where they've upgraded the graphing calculators over time, and they put in the code to make it do the log base for us. Before that, we had to do it this change of base method. So we could do log of 12 divided by log of the base, which is 2. Close. Don't forget to close parentheses when you do that, and then hit enter. Notice it's the exact same number out of that. Okay. So I'm just using the log base 10 button. So you take log base 10, hit this button, type in the 12, close the parentheses, divided by, hit the log base 10 button of 2, and then calculate or enter. And it cranks out the same exact number. So you could do log base 10 of 12 divided by log base 10 of 2, and you get approximately 3.585 again. So you can use the log base way or the change of base way. Either way, it gets the same answer. Okay, so it just depends on how many buttons you want to press or if you want to go through that menu or not. All right, let's do another one. Where that's useful a lot of times is when you have a extremely difficult base, like a 1/3 as a base. So that's saying 1/3 to what power gives me 28. That's a pretty difficult problem to think about because 1/3 to a power is a fraction to an exponent. Makes it kind of tough to do, but we can work this out with the calculator very easily. I'm going to use the log base method because I like the fact that I can do that. And all I've got to be able to do is type in what's written on my paper. Negative 3.033, if we round that. Again, going 3 decimal places there. A nice easy one to calculate would be the natural log of 6. It's a common log. We don't need the log base. We don't need change of base. We've got a button that says LN. Okay, so we just natural log 6, crank it out. 1.792. Log base 3 of negative 20. Okay. I'm going to pretend I don't know something, so I'm going to go ahead and try to work that. Log base 3. Yeah, come on in. Negative 20. What am I getting there? Yours may not have done that. Depends on what mode your calculator's done. If it gave you an error, if you get an error, then you understand that it's probably a non-real answer. Is that what it says? You don't know. Non-real answer. I've got mine set to where it'll actually calculate the non-real answers. But what this tells us is that that's not a real solution. It's a complex solution here, right? And that's a little beyond the scope of Algebra 2. All you got to know is that that's a non-real answer. Okay, so this is the words that the state of Tennessee says you need to put is that's undefined. Okay, so here's why. Logarithmic functions, the domain for logarithmic functions is for positive numbers only. For the real solutions only come from positive numbers. You cannot take the log of 0 or anything negative. That's going to come back when we start doing equations and things where we got to look for extraneous solutions and things. But so anytime, you wouldn't even have to type that into your calculator. You see that you've got to take the log of a negative number or 0, then you know the answer is undefined, or there's no solution. I'll take either of those statements. Okay, so logarithms can only be done to positive numbers. Okay, that's what we're looking for. Okay, easy thing. All right, the next thing is properties of logs. Okay, properties of logs. So what we're going to be doing here is using these to manipulate logarithmic statements. We're not going to rewrite them as exponentials. We're going to rewrite them using logarithms based on these properties. And these properties are going to help us later on when we go to solve equations. We'll go over that lesson tomorrow. To be able to take a fairly complex looking equation and condense it down into an easier problem to solve. So that's what the properties do for us, okay? So the first property that we want to talk about is the power property. And you don't have to know the names of these. You just got to know how they work. Okay, I'm going to name them, but you don't have to know the names. I'm not going to give you a quiz over the names. All right. The way this property works is you've got a logarithmic statement, and it's the log. It doesn't matter what base we're using. I'm put a B there for base. It doesn't matter. It can be log base 10. It could be log base 762. It doesn't matter what the base is. This property holds no matter what the base is. And you have something inside the log that has an exponent on it. Thus, the idea of a power. Okay. What the property allows you to do is take this exponent and drop it down to the front and turn it into n times log base b of m. Okay. What's easier to undo, multiplication or exponents? Multiplication's a lot easier. What's the opposite of multiplication? Division. That's easier to undo than like a third power. You got to take a cubed root to get rid of it. But multiplying by 3, all you got to do is divide by 3. Dividing by 3 is much easier to do, right? So that's one of the properties that can help us solve an equation much easier by just knowing how to do that. Okay, so that's what the power property does. That's what my 4-year-old says. What's it does? Well, it does that. So let's do the product property. The product property takes a log. What's a product in math? It's a multiplication problem. So it takes a multiplication problem, let's just say m times n, and it converts it. Think of exponentially. When you multiply, just for example, x squared times x to the third, what's the rule? Add the exponents. When you multiply, you add. So with logarithms, they're multiplying inside of the log. What that allows us to do is convert this into log base b of m plus log base b of n. It takes that logarithm and splits it apart into 2 smaller logs that are added together. We're going to go expansion and condensing. So the property, though, works in both directions. Okay, multiplication becomes addition. Multiplication becomes addition. I'll say that again. Multiplication becomes addition. Quotient property. What's a quotient? Division. If multiplication became addition, what do you think division becomes? Subtraction. So it's log base b of top minus bottom. Okay. So the product property takes multiplication, makes it addition. Division, the quotient property, turns into subtraction. Okay. Those are the properties that we're going to utilize to work with these logarithms. Okay. So we're going to do 2 things. One of the first thing we're going to do is we're going to expand. We're going to take a single logarithm and stretch it out using these properties. The next thing we're going to do is we're going to condense. We're going to take one that's stretched out already, has addition, subtraction, all those sort of things in it, and condense it down into a single logarithm, which is the more useful way of doing things. The reason we do it both directions, it helps you learn those properties better. Okay, so let's do the expansion first because I think it really helps you learn the properties better. Expand into a sum or difference. So we're going to start with, I don't know, have any clue what letter we're on. Log base 3, not that the base matters, but that's just the base we're dealing with here. Of x to the 7th power. This is a short and easy one because we only have an exponent. Where can that exponent go using our properties? In the front. 7 log base 3 of x. And we're done. That's all that one had. Had an exponent, so you could drop it down to the front. Okay, that's a useful thing. Let's do log base 2 of 3x. What's going on between the 3 and the x? So that turns into, if the product property tells us that multiplication becomes addition. So log base 2 of 3 plus log base 2 of x. We're stretching that out. That's what expanding does. Let's do another. Do what? I need it today. I'm dragging. Be okay. Am I not enthusiastic enough? Today's not one of those days. What's going on in this problem? Division, which turns into subtraction. We got log. Technically, it's base 10. So log. Change colors. Log of x minus log of y. Always numerator minus denominator. Make sure you keep it in the right order. Okay. Let's combine it. Log base 6. 5x to the third over y. Ooh, it's got everything. So, what's the big thing that's glaring here? Division, the big fraction. So we can undo that part. So you can undo these one step at a time, or some of you, as you do more of these, you'll be able to do more than one step at a time. So I'm going to take this one step at a time since it's the first one. So it's going to be log base 6 of 5x to the third minus log base 6 of y. Okay, I've taken care of the division part of the problem. Now I need to take care of any of those individual pieces that will expand. So the log base 6 of y, there's nothing else going on with that one. So I know that's not doing anything. But the first piece, the log base 6 of 5x to the third, has got a lot going on with it. It is doing what? Multiplying. What's multiplying? 5 and x to the third. So we have two pieces that can break into. So that's going to be log base 6 of 5 plus log base 6 of x to the third. And then we still have the log base 6 of y that we're subtracting. Okay, so I've taken that a second step and split that multiplication up into addition. Is there anything else that can be done? Yeah, that product property would allow me to drop that 3 to the front. I'm perfectly fine with you doing more than one step at a time. I'm just doing one step at a time here, notes-wise, so that we can see every individual thing that's happening. Plus 3 log base 6 of x minus log base 6 of y. And that's our final expanded form for that particular problem. So, took a single log, stretch it out pretty good ways there. Log base 2 of y to the 5th over 4x. So, a similar problem, but with a pretty key difference. Literally. So we see division, we see exponents, we see multiplication happening in there. So where do we want to start? Division. That's always where I always try to start, is get rid of that big ugly fraction part, because that's the part that makes it look hard. All right, so what's going to be in the front? Technically y to the 5th, right? But can I go ahead and do that power property? Yeah, so we could put that 5 there. So anytime I can do that, I try to, go ahead and, because the numerator is always going to be the first part, and because it has an exponent of 5, I can drop it to the front through the power property, so it allows me to do that. Okay, and then I'm subtracting log base 2 of 4x. I'm going to take an extra step in here for that part. Now, we've already done the power property on that first part, so there's nothing else to do with the first one. But the second one has what going on? Multiplication. So I've got 5 log base 2 of y. And then I'm going to split this part into log base 2 of 4 plus log base 2 of x. Why did I put it in parentheses?
Because if you did, it would be like the first set minus log. Like those two go together.
Those two go together because they're both being subtracted, right? So this is one way to write the answer. What's another way? It's also accepted. 5 log base 2 of y minus log base 2 of 4 minus log base 2 of x. Why is that the same thing as the line above it?
It's a negative log.
It's a negative in front of those parentheses, so it's like I distributed the minus sign to both pieces. In the original problem, both pieces were divided by, right? So in the expanded form, that both pieces should be subtracted, okay? So anytime you're looking at these, and this is going to help you when you go to do the condensing in just a minute, is anytime you see a minus sign in front of something, it's going to go in the denominator. Anytime you see a positive piece or a plus sign in front of something, it's going to go to the numerator, unless there's some parentheses involved. Okay, you just got to look for those things. So it just takes a little practice of getting there. So let's look at one more expansion, and then we'll get to condensing. Natural log 10 x to the 4th cubed root of y. This one is a... Does anybody know how to write the cubed root as an exponent? You might remember that from exponent rules. What's the exponent on the y that's on the inside? It's a 1, right? So whatever exponent's on the inside is the numerator of the fraction, and the index on the root is the denominator of that. So rewriting the cubed root of y as y to the 1/3 can help us when we go to do our expansion. It'll also help us when we do some condensing later. Okay, so knowing that little exponent rule is helpful. All right, so let's start breaking that up. So we got natural log of 10 plus 4 natural log of x, right? Because we could drop the 4 down for the x because it's got an exponent. The 10 is multiplied times x to the 4. But then that's also multiplied times the cubed root of y, which we know is actually y to the 1/3. So what could go to the front? 1/3 natural log of y. And that's expanded all in one step. That's how I don't know that I would ever do that one with more than one step. Because it's all multiplication. So it's all ends up being addition. Okay? All right, let's work on condensing, which is the method that you really are going to use more when you go to solve equations. Condense to a single logarithm. Yeah, we're going to get through the whole alphabet today, I promise. And a little bit past that, actually. Wx. All right, so log base 2 of x plus log base 2 of y plus 5 log base 2 of w. So just working on properties here and how to condense with that, and then tomorrow we'll start putting this together with solving equations and how that can be useful. All right, so everything is what sign here? Adding, and this piece in the front is what kind of log base 2 of x? Positive or negative? Positive. So it's positive. Everything else has a plus sign in front of it. So we know this is all going to turn into what? Addition turns into multiplication, okay? So when we condense, addition turns into multiplication. The division comes from subtraction, okay? So we know everything's positive here, so it's going to end up multiplying together. Everybody's got the same log, so we know we can put it all together. So we know that we're going to have log base 2 of x times y times what? W to the 5th. Good job. And that is condensed down to a single logarithm. Very, very easy example. Okay, condensing is not hard. Log base 7 of 3 plus 2 log base 7 of x minus log base 7 of 5 minus 3 log base 7 of y. All right, so a lot going on with this one, but they're all log base 7s, so that means they'll all combine into one single log. But what do we notice about it? There's 4 of them, and some of them are positive, and some of them are negative. So that means we're going to have what? And multiplication, division and multiplication, because we got some that are pluses and some that are minuses. What did I say about anything that has a minus? Where's it going to go when we condense? Into the what of the fraction? Things that are subtracted are going to go to the bottom, into the denominator. Things that are positive are going to go to the numerator. Okay? So when we look at that, it can help us know, hey, these two things are going to go together, and these other two things are going to go together in a different spot. Okay, so we look at those. What's going to go in the numerator of the fraction? 3x squared. So we're going to have log base 7 of 3x squared, because the 2 that was in front of the log base 7 of x goes up as an exponent, and then we're multiplying 3 times x squared because they're both added. The denominator is going to be the minus stuff. So we have 5 and y to the 3rd. What are they going to be doing in the denominator? Is it going to be 5 over y to the 3rd like that, or 5y to the 3rd like that? And why is it that one and not the other? Yeah, because in reality, this is minus and then log base 7 of 5 plus 3 log base 7 of y. That's really where that's, because they're both minus signs. Anytime you have multiple minus signs in there, you're going to combine those with multiplication out of that. You're not going to do a double division. There's no double divisions. Okay. So if you'll just remember that, it's no double division in condensing logarithms. And then we have one single logarithm. I don't know if we've ever gotten to all of the alphabet with you guys. Doesn't matter. Well, let's do natural log. Change the base here. Plus 5 natural log of x minus natural log of y plus 4 natural log of w. Randomize it here a little bit. So we're going to condense that into one single natural log. So what's going to be going on?
Well, they're all natural.
I got you there. I'm ahead. Glad you were listening.
Okay, so you're adding the first ones,
Okay.
That means they're multiplication.
Okay.
No, they can go on the top.
So that go on the top. All right. So
4x to the 5th.
okay.
And then y w to the 4th, right?
Where does that go?
On the bottom.
Both of them?
W to the 4th goes on the top.
Why does it go on the top?
Positive.
Yeah, it's got this plus sign in front of it. So that's why the W to the 4th is going to go on the bottom. That's right. What's the only thing that had a minus sign in front of it? The thing with the Y. So that's why it's going to be by itself in the bottom. They can get you with those when especially when you have a couple of them in a row like that. And they don't put parentheses in there, very different problem. If you do the same problem, so our next example, we'll call it AA. But I'm going to put parentheses in it. So exact same setup, except for it's got parentheses in it. What changes?
The W.
Yeah. That's right. That's right. So you got 4x to the 5th up top, and then yw to the 4th. The parentheses make the difference on what all goes to the bottom there. So paying attention to parentheses is very important when you start condensing logarithms. Let's do one more, and then we're done for the day. Log of 8 plus 2/3 log of y minus 6 log of x plus 3 log of z. Several variables here, but obviously when we go to do equations tomorrow, we'll just be dealing with various pieces that have the same variable. Properties wise, it's easier to think here when you got different pieces. So this kind of relates back to the last two examples. It's just got a little extra thing in here. What's going on?
Are we gonna have a cube root thing?
Why would I have
Because
that?
it's 2/3.
Okay, so we got a fraction and a power rule, so that's going to become an exponent. So yes, you got a fraction exponent. So let's go ahead and condense a little bit, and let's write it with the exponents, and then convert back to a root before we do that. But yes, you're right, absolutely. So what all is going to be multiplied together? And I see a minus sign, so that makes me, I got to have a division in there somehow. Right? So log, what goes on the top? 8 y to the 2/3 and z to the 3rd. And then what goes on the bottom? X to the 6th. Okay, so there's one way to write a solution there using exponents. But Lily Beth is right. That fraction exponent, usually we want to convert those back over to roots and convert that. So the 2/3 power, that's going to be the same as log base 10 of 8 z to the 3rd. And then the denominator's a 3, so that means it's a cubed root. And then it's got a 2 as an x as the numerator, so that's y squared inside and x to the 6th. On a quiz, I'd take either one of those as a solution, but understand like multiple choice type format. This is correct, but they may not have it written that way. They may have it written with roots. Also understand they may not have it written as the roots. They may have it written as the fraction exponents there. So either of those is actually correct, but know that both of those could be solutions to that. All right. So